Testing. 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 All right. All right, we are live. Okay. So welcome everybody to another Hoop Host stream today. Today we're going to be doing a little bit of a paper stream. The paper drought is over, and now we're starting to get conferences coming in. So this is coming out as SIGGRAPH Asia. I think this conference is Korea, and most of this work is out of Princeton. Actually open this in lighting in. So this is coming out of Princeton University. Submission to SIGGRAPH Asia. And I thought this was an interesting one because it's a slightly different way of doing NeRFs, and I'm always interested in NeRFs. Point-based representation. See here, they're comparing it ground truth, I guess is a mesh something, and then they have theirs, which is point-based. They have NeRF, and then they have planoxyls. This was the more interesting one here. So they have basically a NeRF video. You can see how the NeRF variations have this kind of like fuzziness that you often see in NeRFs, but the one that they show is actually quite clean and quite crispy. Yeah. I don't quite know what ST-NeRF and NeRF-T are, but we'll see which one of those are. We'll probably link. But yeah, it was interesting enough for me to go ahead and peg it, and let's review it. Okay. So novel view synthesis with differentiable point-based radiance fields. You introduce a scene representation that models radiance. So this is a scene representation, right? Like a NeRF, you're basically getting a neural net to learn or encode all the information within some amount of 3D space. In this case, it's modeling radiance with a point cloud augmented with local spherical harmonic coefficients per point. All right, so this is the stuff that we were reading about before, these spherical harmonic coefficients, which is basically a mathematical abstraction that is actually used to describe electron density clouds. So it has use in physics, and people use it in are increasingly using it in NeRFs because it's a good way to represent the object in 3D space, right? Or not an object, but a probability cloud in 3D space. Representation is not only memory efficient, but also 2 orders of magnitude faster. Okay, so they're basically saying memory efficiency and faster in training and inference than a coordinate MLP-based approach that relies on ray marching. So coordinate MLP, this is basically what a NeRF is, right? Where you have a multi-layer perceptron or an MLP or a neural net, fully connected neural net that takes a coordinate, right, a certain position in 3D space, and then will tell you what the opacity and the color is of that, and then given that neural net, you can basically do ray marching, which is a type of rendering. But again, the hard part of that is that you have to basically, for every pixel in the image, you have a ray, and then for every ray, you're going to have a variety of samples along that ray. So one of the big problems with NeRF is just how compute heavy it can be. So people are kind of going around trying to find more efficient ways to do this, and this paper does seem to propose one of those. In contrast, the proposed method allows for efficient view synthesis via differentiable splat rendering. Okay. Don't know what that is, but we're going to learn about it. We test our method on novel view and novel view video synthesis task, where it outperforms existing methods, including recent NeRF-based approaches, shown here for multi-view video data in both quality and runtime. So, compared to other Zhang et al., and this paper is Zhang et al. I don't know if it's the same Zhang or not, but I think it's a common last name, so probably not. Propose a differentiable rendering algorithm for efficient novel view synthesis by departing from volume-based representations in favor of a learned point representation. That's really the big novelty here, is that they're going away from kind of what NeRFs do, where they represent a whole volume, and they're going to learn point representation with harmonic coefficients. We improve on existing methods more than an order of magnitude in memory and runtime, both in training and inference. The method begins with a uniformly sampled random point cloud. Okay. That's what it starts with, and then learns per point position and view-dependent appearance. A differentiable splat-based render to train the model to reproduce a set of input training images proposed. Our method is up to 300 times faster than that is huge, but I mean, there's also some implementations of NeRF are 100 times faster than other implementations of NeRFs. So we'll see if they just pick the worst possible implementation of NeRF to compare it against. While using less than 10 megabytes of memory for a static scene. For dynamic scenes, which basically just means a video or a time-based component is added to a 3D scene, our method trains 2 orders of magnitude faster than ST-NeRF and renders at near interactive rate, while maintaining high image quality and temporal coherence, even without imposing any temporal coherency risers. Temporal coherency regularizers, I guess, is any kind of regularization loss that you can add that ensures that from frame to frame in a dynamic scene that the elements are consistent. So this is SIGGRAPH Asia 2022, which was held in Korea. And I think Princeton itself isn't. So neural rendering has emerged as an effective tool to model real-world scenes, synthesize novel views, and advance single-shot learning. Existing work has made it possible to generate photorealistic novel views at unseen viewpoints from unorganized multi-view training images. I don't know about the word unorganized here. I think that in order to train any kind of neural rendering, you need to know the camera position very well. So it's not unorganized multi-view training images. It's well-defined training images. Synthesizing novel views can not only enable aftershot visual effects, but also implicitly entails the geometric understanding of the scene. This is also kind of another potential negative of NeRFs, is that you don't have an explicit representation of the scene. So like if you ever wanted to do physics or kind of any interaction, right, like you see in most video games now, most objects have some kind of physics to them. It's there's no thing that I've seen that tries to do that with NeRFs yet, because there's no such notion as object boundaries and mass and so on. NeRFs spearheaded neural rendering by modeling a 5D radiance field in a memory-efficient manner. So the 5 dimensions here are the x, y, z position of a point, and then the U angle, right? Or they could also be referring to the color and the opacity. A large body of work has built on this method using implicit scene representations for view synthesis. However, a drawback of modern neural rendering methods is their computational efficiency. Very expensive. Typically more than 100 evaluations per ray. Right, and then there's 1 ray per pixel. NeRF takes over 10 hours of training and 30 seconds of inference for each scene on a single GPU. I think there's works that do it significantly faster, but sure, that's kind of somewhat fair. Recent methods have attempted to tackle this problem by pre-training a multi-view stereo model on a large-scale dataset and fine-tuning it to input. Explore an alternative approach for retraining a highly desirable end-to-end differentiable. Though the MLP used by NeRFs is compact and relatively efficient to evaluate once, using it for image synthesis is fundamentally a backward mapping operation that requires multiple evaluation gradients. Ray. Okay. Shifting to a representation that allows forward mapping, i.e. creating an image via a single forward pass over a representation radiance field, enables modest gains in storage, but more importantly, efficiency gains in multiple orders of magnitude at both training and rendering time. Okay, so this is an interesting take where it's basically saying that NeRFs are very kind of like almost microscopic, right? Where every single tiny point, you have the smallest possible little multi-layer perceptron being used at the kind of smallest discretization of space in the 3D volume. But what they want to do in this work is say, okay, well, actually, let's put the neural network at the highest level, right? Where basically the output of the neural network should just be the image. Right? Create the image with a single forward pass versus a NeRF where you're using the neural network to give you the color at a single point on a single ray or a single pixel. So kind of flipping that that idea of where should we put the neural net in this system? Where should we try to learn a function that approximates? Right? Because that's ultimately what you're doing with a neural net is you're basically just using a bunch of data to learn a function. Use a representation for radiance based on RGB spherical harmonic coefficients stored at points in 3D. Image synthesis is then accomplished via a differentiable splat-based rasterizer that operates as a single forward pass. Rendering pipeline from point primitives and spherical harmonic coefficients to images is end-to-end differentiable. Okay. So differentiability is required for using the gradient descent method that basically everyone uses to train a neural net. So if you have a relatively complicated pipeline, you want to make sure that every part of that is differentiable so you can push the gradients through. But everything they're going to be doing here, it's all just geometry and math and kind of stuff like that. So all of that is differentiable. Okay. Our strategies yield several benefits: smaller storage, faster training, and more rendering. Okay, so they say that basically it's very fast and it can work with not a lot of data, but if you have a ton of data, then the NeRFs actually are a little bit better. Okay. Our approach learns point clouds with position and appearance without a neural network or separate geometry estimation via ColMap. So ColMap is basically a way to get camera position from a series of images of a static scene. So it's more of a kind of classic computer vision algorithm. It's been used for a while, and people will use it to basically say, hey, I have a bunch of pictures of some object or some scene, and I want to know where each of these pictures was taken from. So obviously, if you're training a NeRF, whenever you feed the training data into your pipeline, you need to know exactly the corresponding camera position for each image. And a lot of times they'll just use ColMap to do that. But here they're saying that they don't actually need that, so they don't have to do this ColMap step, which makes it faster, because that's one less thing you need to do in this pipeline. Okay, so here are their main contributions in machine learning papers. Generally, basically, you have your abstract, your introduction, and then at the end of the introduction, the authors will kind of put a bulleted or a numbered list of what they say their contributions for this paper are. So you can always skip down to these little bullet points if you know more specifically about what they're doing. Okay. So they introduce a point-based radiance representation that, together with differentiable splatting, is 300 times faster. Okay. So a different type of representation than a NeRF. So it's different in that it's a point-based radiance representation, and then it's also faster. We analyze in terms of memory, efficiency, inference, and runtime, and show that it outperforms state-of-the-art neural rendering algorithms. Okay, but only in compute. So they're really trying to sell you on the speed and memory efficiency of this. We demonstrate that our method is efficient enough in memory, training time, and rendering time to enable novel view synthesis for video, even without establishing explicit frame-to-frame connections. We validate that the proposed method outperforms existing methods in quality, runtime, and memory footprint. They just keep on and on going about basically Okay, limitations. The proposed method requires an object mask. Oh. That's no good. And thus can only render the foreground scene components. Okay, so that's good to know, where you can't have a scene with a background. You can really only do individual objects that are masked. So you see everything here is on a white background. Good on them for kind of saying that. Okay, so even though it has this limitation, they say limitation may potentially be listed by replacing the hard multi-consistency function. So there's probably some kind of regularization loss here that that kind of promotes multi-view consistency, and they say that if you replace it with a soft one, it does a little bit better. Proposed representation, which relies on splatting, can also not handle transparent objects, e.g. objects with. Okay, so also a limitation is things that don't have kind of hard edges, right? So yeah, if we look at their examples, every single one of them has. Actually, maybe not, because this, like, tree leaves are also difficult to do, right? So if you get tree leaves right, that's probably fine. Right. Onto this section here, related work. Neural rendering. A rapidly growing body of work investigates introducing differentiable modules into rendering approaches, turning conventional rendering methods into powerful volumetric rendering. Various neural network architectures have been proposed to model scene radiance, including convolutional neural nets and neural volumes. Okay, so multi-layer perceptron and NeRF. This is the original NeRF paper, I guess. While the synthesized image from these methods achieves unprecedented fidelity, one of the drawbacks is their generalizability. Yeah, so, I mean, pretty much all NeRF papers and neural rendering papers at this point, like, they're trained on a single scene, right? Another line of neural rendering uses a multi-plane image as a scene representation. I think this is the one we read, where they had basically multiple volume, and the intersection of the rays with those planes were where the sample points were. NeRF-based volumetric methods have achieved remarkable success. Yeah, so NeRFs are really kind of the king in this category right now, which is why this paper is interesting, because this one kind of proposes something different. NeRF-based models typically require hours of training on a modern GPU, and it's only for a single scene too, right? So you have, it's kind of a limitation where it's like, you want to get to the point where you're going beyond static scenes, you're going to dynamic scenes, and then you're going into dynamic scenes where there's objects coming in and out of it, right? Like in a video game or in a movie or anything like that, right? The amount of stuff going in and out of that is very complicated. Here. Do you have anything to say? No? Okay. I thought maybe she wanted to say something. Okay, recently researchers have devised methods to accelerate inference. Okay. The octree structure, I think this was the NVIDIA paper where they got a 10x improvement. Replacing large MLPs with multiple small MLPs, so basically making the little neural nets faster, or smaller so they can be faster. Lombardi hybrid scene representations with primitive-based and volumetric components. This might have been the ones we looked at. I don't quite recall anymore. This method inherits some of the drawbacks. This work requires 5 days of training time for a single scene. Crap. What? Of a depth oracle to speed up the model training. So this is basically just, you know what the depth is. So depth, you can get it from like a any kind of like structured light sensor or LiDAR or anything like that, right? You can do it from just camera images too, or a stereo camera. But if you know the depth, if you know what each pixel, the distance from each pixel to the camera, that can help you train faster, because it's an additional learning signal that you can use. So that's what that means there. Use of a depth oracle just means they're also training on depth. It's not just an RGB image, it's an RGBD image, where that D is depth. Gigabytes of memory consumption for each scene. That is true, and it's also very sensitive to the image size. Okay, so in this work, this paper, they achieve 2 times faster inference, 3 times faster training, and 100 times lower memory. Finally have some numbers on the actual improvements. Work falls into category of multi-view geometry reconstruction methods studied for decades. Vision. This direction traces back to popular multi-view stereo methods using local photometric consistency and global visibility constraints and geometric priors. I think the key is the geometric priors here, right, where they're going to show you that the spherical harmonic functions are basically a very good geometric prior. The same way that ConvNets used the convolution operation as a geometric prior in 2D images, I think that 3D problems are also going to very much be enabled by good geometric priors. So you see a consistency here on anything 2D or 3D, anything where you're like dealing with kind of real world things. Having a good prior can basically make all the difference. That's what we saw with convnets, and that's what we may see here with these spherical harmonic functions. Okay, Wiles and Ponut propose single shot video prediction mesh-based methods. Typically require a separate data set. Train the model for a geometry prior. Knowledge of the visual wall. So I guess that's the mesh. Okay. Surface lights field is based on a view-dependent level of detail rendering for subdivision. Using spherical harmonics in this context has been proposed as an effective way to represent a view-dependent function with a broad adoption in rendering and modeling. Recent works apply view-dependent models to reflectance via implicit BRDF modeling. Okay, so there's a couple other works that also use this spherical harmonics. It's not like an original idea by these authors. This is something that's been used in computer vision pipelines for a while now, although it's definitely pretty niche and obscure. All right, and then the final kind of related work section that they have here is on point-based rendering. So point-based rendering via splatting. Click on that. Has been explored for decades, offering computational efficiency as elegant scene representation. Recent works explore combining deep learning with surface splatting, differentiable algorithms for this. And once you have something that's differentiable, then you can basically push gradients through it. Proposed method optimizes for point positions and spherical harmonics, coefficients, and fashion. And it focuses on high-quality image-based rendering and novel view synthesis. Okay, so basically kind of the difference here between a couple different works is some of them have, like, the input data is different, right? Here in a Leaves paper, you need the point cloud. Here you go, another use of ColMap to build a point cloud. And another kind of classic computer vision algorithm to build the depth normal. So depth is basically for each pixel you the distance from the camera to the pixel, that's the depth. You've ever seen that? So this is what a depth image looks like, right? Something like this. And then normal maps are basically the vector that is up. So this would be a normal map, right? It's telling you what is pointing up and what is the, like, basically the angle of that surface. So Sibber here allows you to get the depth and maps from. Very recently, PointNeRF proposes a point-based rendering method, which in contrast to the proposed method is not network-free and relies on relatively slow volume rendering. Okay, So now they're going to get into the actual meat here. And the first thing they're going to talk about here is differentiable point radiance fields. So in this section, they describe the proposed differentiable point-based rendering method, illustrated. So they assume a set of images ij, where j equals 1 to n, so there's n total images here, with known camera intrinsics and extrinsics. Okay. So intrinsics are basically the parameters of the camera itself, such as focal length, right? Basically, like how much distortion is happening in this camera, right? Different cameras have different field of views. They have different amounts of distortion, different types of distortion based on the lenses. So that's what camera intrinsics are. And then camera extrinsics are external, right? So it's basically where is the camera? What is the position of the camera, the pose of the camera relative to everything else in the scene? So basically, they have a set of images, pictures, and then they know exactly what the camera is and all the information related to the camera, including the camera internal properties and the camera external properties, right? Internal intrinsic, external extrinsic properties. We learn a model of a scene as a point cloud with a per point radiance model based on spherical harmonics. Learning minimizes the difference between the rendered scene and the original images. So basically, ultimately your gradient is coming from the fact that you know what the real image is at that viewpoint, and then you're basically comparing that to the image that your pipeline generates. By updating the position and appearance of each point. Okay. The use of a differentiable splat-based rasterizer allows for gradient-based updates while being orders of magnitude more efficient. The point cloud the proposed method is operating on is optimized end-to-end in a coarse-to-fine iterative fashion, starting from a rejection-sampled initial point cloud. Okay, so learnable point cloud. Let's look at figure 2 here. So I think that the main kind of difference between this and a NeRF, right, is that in a NeRF, you basically have a volume of space, and then any point within that volume of space, your neural net will tell you what that point looks like. And then over time, your neural net is basically building this internal representation of what that scene contains. But it seems like what they're doing in this paper is they have an explicit actual point cloud. They start with an actual point cloud, and then they're basically adjusting each of the little points in that point cloud so that it matches the scene. So you can see here that the this hot dog with the things, right? The scene is actually explicitly represented as little points, right? And you can see how each of these are little points. The whole plate is a collection of little points, and so on. So learns a point cloud augmented with RGB spherical harmonic coefficients per point. So every single point here has spherical harmonics, and then it has RGB to it. So every little point has a color. Image synthesis is accomplished via differentiable splat-based rasterizer that operates as a single forward pass without the need for ray marching and hundreds of evaluations. So this is kind of the big difference. You don't need to cast a ray. In a NeRF, right, this ray, this black arrow that goes through the point cloud, you would basically have to sample along it. You would have maybe 10 different samples along that ray, and then you'd have to evaluate your neural net at every single one of those samples. But here, you don't have to do that. The point rasterizer computes an alpha value from the ray point distance with a Gaussian radial basis function weight. Okay, so there's some alpha value for each point. The learnable radiance in the alpha values, okay, are rasterized via alpha blending to render the image. The entire rendering pipeline is differentiable, and we optimize for the point position and spherical harmonics coefficient end to end. We use a hybrid coarse-to-fine strategy to train the entire model and successively refine the geometry represented by the learned cloud. Okay, so you have here different points, P1, P2, P3, P4. I think these are different points that are intersected by this ray. I think these like blue and red blotches inside these circles, these are the spherical harmonic functions, right? Kind of an image that shows you that, and then the coefficients would be the parameters that parameterize the functions that end up creating these blobs here. And those are what you're learning, but you're also learning this alpha here, right, which is a distance. So they basically have this bracket here that says, okay, the distance between the ray and I guess this point here, within that is some Gaussian, and then that leads to alpha. So the ray point distance, Gaussian, okay, never mind. This is not the spherical harmonics. This blue and red stuff is the Gaussian radial basis function, I think. Okay, rasterization is basically just going across. So let's see if we can find a good picture. None of these pictures are good. Okay. Hopefully they have a good picture to explain or a good example. But ultimately, this whole pipeline here is going to give you a predicted image, right? Predicted pixels, predicted RGB. And because you actually know what the scene looks like from that position, you have a ground truth image, and then you basically, your loss compares the predicted RGB with the ground truth RGB, and then you basically backpropagate that all the way through here because everything is differentiable. Okay, let's actually get into this point-based scene radiance that they have here. Model the scene as a set of points, E sub I, Xi, Yi, Zi. Okay, and T just is the transpose there. So there's lowercase n points in 3D space, right? So there's capital N set of images that are used to train, but then there's lowercase n set of points with the parameters hi of a view dependence radiance model per point. So there's going to basically be different parameters for each point. So however many points you have in your point cloud, you're going to have a different set of parameters to represent that point. These 3D positions and radiance model parameters serve as the unknowns that will be updated by the optimization method to reach the scene. Okay, so not only is your optimization, right, your gradient descent, the learning that you're doing, not only is it updating the parameters of this radiance model, but it's also updating the actual point positions, right? So it's actually, over time, you're actually moving these little points, which is interesting. Each 3D point Pi projects into a 2D position Pij in each image ij. Okay, so each point here, right, each little blue and green has some 3D position, but it also has a 2D position where the 2D position is in pixel space. So it has a 3D position in world space, and then it has a 2D position in pixel space, right, in image space. To model the projection operation, we assume that we know the extrinsic rigid body transform and intrinsic matrix for the camera. Okay, so basically this is what we were saying before. They know everything about the camera. They know the relative position of the camera to the scene and to every picture, basically. And then they also know the amount of deformation in the camera, the focal length of the camera, the field of view of the camera, and everything else associated with it. So from that, you can basically say the 3D position of the camera is related to the 2D position of the camera by basically just taking the rotation of the camera, the translation of the camera, and then the intrinsic matrix, which basically warps it correctly. So this is just kind of basic camera math and geometry that allows you to say this 3D point in the scene is equal to this 2D point in our image. Where this little down arrow that they define here is basically just the perspective divide. Here, PI are represented as learnable neural parameters. Note that visibility is resolved by the rendering stage via depth sorting and alpha blending. Okay, so in this method, right, your scene is going to be represented by these points, and we don't know how many there are yet, but there's probably hundreds of these points, right? And your optimization process is learning the position of all these points. So very likely you're going to end up in a situation where some points are behind other points, right? Or maybe points that have a high alpha, right, which means they're very not see-through, and then points that have a low alpha see-through. So when they do the actual rendering here, visibility is resolved by the rendering. What that basically means is that they're going to choose which points actually get shown in the image using the rendering. So there's no, there's nothing in the actual, there's no learnable parameter that is basically explicitly storing visibility or explicitly defining the visibility. We model the view-dependent radiance of each point with spherical harmonics. Okay. View-dependent radiance of each point. So basically the color conditioned on the view. So view-dependent just means what is the color of that point? It's conditioned on the actual position. This is, I guess, the original spherical harmonics paper, Cabral et al. 1987. We can 1980 bidirectional reflection functions, surface bump maps. That up. So maybe we should read the original spherical harmonics paper. Okay, up to a maximum degree L max. So there's probably a view angle threshold. I think that's what this L max is. So what is M? Note that HI, LM here are learnable. And we denote the view direction of point I. Okay, so point I, image J, and this is the view direction here, VIJ. And that is just the vector. So this is a vector here. This is the 3D point, right? Capital P sub I is 3D point. Capital R sub J is the rotation matrix of the camera. T sub J is the translation of the camera. So rotation matrix times 3D point plus 3D point is going to give you a vector. And they're dividing here by the norm of the vector. So this part here, this bottom part, is just basically the magnitude of that vector. So the view direction here, VIJ, is going to be a unit vector, right? A vector that has a unit length 1. And the color of the point is this, CIJ. And CIJ is going to be the sum of, where did they say M? They still haven't told us what this little m is here. I'm looking for the definition of little m, but there is none. Nothing is more annoying than equation sections where they don't tell you what all the different terms are. But, okay, the color of the point is basically you sum over m from negative L to L, right? You're summing over m from negative L to L. And then you're summing over L equals 0 to max. So there's two different summations here. Generally, that's not a good thing because that means that summations are kind of annoying to compute, and double summations are even more annoying to compute. So usually when you see a lot of summations like that, it kind of ends up bad for the compute efficiency. And that's what you see in NeRFs, right? Where you're summing over all pixels, or you're doing it for all pixels for all samples in array. So that's a little sus. We have here the view dependent, or the view angle, capital Y ML. That. They also don't tell us what that is. And then this HILM, where HI is the... Also don't tell us what that is. Okay. They haven't told us what H is. They haven't told us what capital Y is. I think they're the spherical harmonics, if I had to guess, right? Spherical harmonics, HI, and then Y. So I think these are basically the parameters of a spherical harmonics function, if I had to guess. We initialize points randomly within the visual hull defined by the image space masks. Specifically, we use a rejection sampling method in which we uniformly sample random 3D points, project them into each image, and keep them only if we fall within all the masks. Okay, so this is how their scene representation has every 3D point, right? And they're over time adjusting the positions of these 3D points and the view-dependent radiance, which is just basically the color of the 3D points. And then whether or not they actually render is... They'll basically do what they're calling here rejection sampling. So they're sampling and then they're rejecting. So they uniformly sample random 3D points in here. So, right, there's hundreds of points here, and they're going to randomly sample some of them. And then they project them into each image, right? They can just use this equation 1 here to say, okay, does this 3D point, what is the position of this 3D point in the image? And if the position that it is in the image is not within the mask, right, because they said that there's a mask for each image, then we're just going to reject this point. So there's a lot of the kind of like random sampling and then rejection if that point does not fall within the mask in the 2D image space. Visualize the point appearance by sampling the spherical harmonics parameter from the normal distribution. Okay, so zero mean and standard deviation of 1. So the spherical harmonics parameter, right? They're learning the position of the 3D point, but then they're also learning the parameters HI, right, which parameterize this spherical harmonic function. And there's different ways to initialize parameters when you're learning, right? Like, for example, for a neural net, you might use Xavier initialization. But here, they're basically just going to, at the very beginning, they're going to start with a normal distribution with zero mean and standard deviation of 1, which is basically the most generic thing you could normalize anything to. Our method is thus dependent on the availability and quality of the initial masks. So it'd be interesting to know how they get these masks, right? Are they taking real-world images and using a separate segmentation model to get these masks? Or are they using synthetic data at which point they have the actual true mask? Okay. Differentiable splat rendering. Okay, so this is the thing that we didn't really know what this was, but here we're going to get a good example of this. So, given a point cloud model, re-render an image via point splatting. Okay, so here they reference Zwicker et al. For a background on splatting method. So this is probably the original background splatting paper, which is 2001. So, interestingly, right, if you look at deep learning, so many of the things that we do now, there's actually papers for them that were written in the 80s and 90s, right? So before we had the compute available, people were already exploring kind of the theory and the math space for different deep learning approaches. And there's a similar thing for computer vision here, where the stuff that they're using, right? These spherical harmonic functions, the splat rendering, like these aren't original ideas. These are ideas from 1987, from 2001. So there is kind of a recurring pattern here where you can take stuff that people were doing 20, 30 years ago, reapply it to the current stack, right? Use PyTorch, use GPUs, use more data, and then you actually end up getting pretty good results. So this kind of motivates the idea of like performing paper archaeology to find original things that maybe were forgotten and are lost in some dusty corner, and actually trying to apply them with modern compute and see if you can get anywhere. Specifically, we use an image space-based radial function kernel, radial basis function kernel, image space. So I think that's what this blue stuff here is. Inside of these circles, which are aligned, right, orthogonal to the ray, which means that they're in image space. They represent the contribution of each point, Pij, to each pixel U in an image J. We employ a Gaussian kernel of radius R. Okay, so there's some radius R, right? And the radius R of a Gaussian kernel, you can kind of visualize that in your head as basically the kind of standard deviation from the center, right? So it's like if you imagine a center line cutting through a Gaussian, right? The distance from that center line to kind of this point here, that's roughly analogous to kind of the radius of a Gaussian kernel, right? Okay, and then it computes the opacity. So opacity is just the alpha, which is basically just how see-through something is. And that is 1 over 2 pi r squared e to the negative, this is the point in pixel space, right? So U is the pixel. So this is the pixel space position for the point. U, which is the actual pixel position. So basically, how far away is this point from the center of the pixel squared? So that's kind of like an L2 distance there over the radius. So basically, this is like a rough estimate. Like this function, what it's largely doing is it's basically saying points that are close to this pixel and this ray and this Gaussian kernel will have a high transparency, or not high transparency, will be much more solid, right? And points that are further away from this pixel and this point will have a higher transparency. So at the very center of this Gaussian kernel and at the very center of this point, it'll be very solid, and then as you kind of go outward from it, it'll be increasingly more and more transparent. And if you do this for every pixel in the image, eventually you get the alpha map, which is basically just the transparency for every pixel in the image. We sort the points by z distance and compute the final rendered image ij. Final rendered image ij via alpha blending from front to back. So what is alpha blending here? Alpha blending is just finding, I think this is the alpha, so the alpha for that pixel times C sub ji, where, what is C? C is the color. So the transparency of that pixel times the color of that pixel, and then you sum it over all pixels in little n, right? This little n, which is basically, we saw here, little n is the number of points. So overall points. A sub I sup j u represents the net contribution of the ith point. Right, so different points are going to have different contributions because the Gaussian kernel here, right? In the center, it's going to have a high alpha, but then as you kind of go out towards the edges, it'll become more and more see-through. So in order to get the actual final value for a single point, you're going to have a couple different kind of see-through parts concatenated, right? Or not concatenated, but summed, or in this case, multiplied. So you have here the transparency for a single point, right? Lowercase alpha here, transparency. You have the summation, or the multiplication. This is just, this giant pi symbol just means multiply. It's kind of like the summation symbol here in equation 8, but it's multiply of 1 minus the alpha, right? So this is point k. So you multiply all the alphas, or 1 minus the alphas, times the alpha of point I. Points are taken as sorted front to back. And Cij is the per point color. Note that as an optimization, we only consider points with a certain maximum distance of U with non-negligible opacity. Okay, so they also have thresholds for opacity or transparency, at which they just kind of throw it away. And then they have a threshold for distance U, which is basically once you get past a certain distance from this pixel in pixel space, then we don't actually care about the contribution from other. All right, section 3.3, point cloud training. Train a point cloud that predicts the image I sub j. We employ a loss function incorporating the MSE loss and the total variance loss. Okay, mean squared error loss and total variance loss. So here you have basically the predicted image, right? That. You have the predicted image minus the ground truth image, right? So here you're just subtracting the two images. And then here, TV of the predicted image is the total variance of the predicted image. The total variance term represents the conventional anisotropic total variance penalty. Okay, so the TV function, right, is the curl of x, the curl of y. The L1 norm of the predicted image gradients. Okay, so basically this TV is a regularization loss that tries to keep the gradients, I guess, small. And then this lambda here is just going to be a hyperparameter, so that's going to be something that they pick and then tune over time. We are able to learn the point positions and their parameters using stochastic gradient descent. During the method, we propose a non-synchronous learning strategy for optimizing the point position and harmonic parameters. Okay, non-synchronous. The initial learning rate for the spherical harmonic radiance model and the point positions are 3e to the negative 3 and 8e to the negative 4. Respectively. Both of them are exponentially decayed for every epoch. Okay, so you have learning rate scheduling going on here. And the learning rate scheduling is happening with a factor of 0.93. So these learning rates are already pretty small, 3e to the negative 3, 8e to the negative 4, right? The point position has a smaller learning rate than the spherical harmonic parameters. Not only are they small, but they're also very quickly decaying the learning rate. And the number of epochs that they actually use is actually also quite small. 20 epochs total for training this, right? And as we saw in the introduction, like this entire paper, they're really talking about the speed of their approach. So obviously it was going to be a small amount of epochs. The total variance weight, which is basically this hyperparameter that just kind of says how much of your loss is dominated by the difference between the ground truth and the real images, and then how much of your loss is just the this regularization TV term. So that's relatively small. So only 1% of the loss here is coming from this total variation penalty. The splatting radius R and the rasterization N, right? N here is the total amount of points, I equals 1 to N, are set as 0.0008, right? So this is actually quite small. The splatting radius, I think this is in pixel space, so only 8%, or like 0.08% of the image is basically ever related to each other. If that makes any sense. And then 15 points. Maybe N is not that. Seems wrong. There should be way more than 15. Okay. L max equals 2. Section 4.3 contains an ablation study for comparing spherical harmonics to just a single color, which effectively corresponds to L max equals 0. To learn an accurate point cloud representation, we repeat the following several stages of a coarse-to-fine scheme twice. We assume a voxel discretization without actually voxelizing the scene. And for each voxel, we aggregate all the points inside that voxel into one single point by averaging the position and the spherical harmonics of these points. Okay, so they have this huge amount of points, and they want to reduce the points, right? So they want to take this point cloud, and then they want to reduce it, so point cloud reduction. Voxel-based point cloud reduction is basically saying, okay, well, for every little voxel of space, right, which is just like one little subcube. I don't know if I need to define voxels, but right, you have a volume of space, and then like this one little cube inside would be called a voxel. So they're saying for each voxel, we're going to take all the points inside there, average the position and the spherical harmonic parameters for those, and then that'll be the single point. The motivation behind this step is to avoid the formation of dense point clusters and improve the representational efficiency, right? So it's just basically kind of a way of downsampling. Outlier removal. For each point, we'd compute the distance to its neighbors and the standard deviation of these distances. Okay, distance to neighbors and the standard deviation. And then we filter out the outliers whose standard deviation is beyond a threshold. Okay, so more filtering, removing outliers. And then point generation. In this stage, we insert new points into the point cloud by generating a single new point for each point in the point cloud. We set all parameters to the average of the points k nearest neighbors. Okay, so this is interesting. So basically, they're building this point cloud over time, but they're kind of, they start with a kind of a point cloud that doesn't really mean anything, right? It just has a bunch of a normal distribution with zero mean and standard deviation. They apply a learning step to it, and then they go through, they reduce the point cloud with this voxel-based reduction, they remove all the outliers, and then they generate new points, and then they'll push gradients again, right? So I think that's this coarse-to-fine update, they say happens twice over the course of the training, and I think there's 20 epochs. So I wonder whether that's twice per epoch or whether that's twice total with 20 epochs each. I think it's probably the latter. Okay, when extending our method from novel image synthesis to novel video synthesis, all right? So now they're going from static scenes to dynamic scenes. We train a model per frame. So this is kind of the curse of dimensionality of video, that videos are really just sequences of images, which means that for 1 second of video, you might have 60 seconds or 60 frames, 60 images, right? If you're doing 60 FPS. But here, if it's already taking you like 3 hours to train one point cloud for one static scene, if you want that point cloud over time, now for each second, you're doing 60 times the amount of work. Okay. However, in dynamic video scenes, nearby frames are temporarily correlated. As such, we can use the model learned in a given frame to initialize the next frame. Yeah, so they can basically say, okay, well then rather than starting from scratch, we're going to start from the previous point cloud at the previous time step, and that'll allow us to converge a little bit quicker. For a given frame, the proposed method obtains an accurate point cloud S1 with the learned spherical harmonic parameters. Next, we compute an initial point cloud S2 for the next frame 2 using the same scheme. We then compute the chamfer distance, C script CD of S1 and S2. So this is basically just a distance metric for point clouds. So basically for every point in this point cloud, it'll compute the distance, and then it'll sum them all up, right? So you have L2 distance here, right? And then you have a summation over all points in S2 and over all points in S1. So that is basically just a distance function between 2 points. By minimizing the chamfer distance via gradient descent, specifically the atom optimizer, probably just the PyTorch implementation of that with the default parameters or default hyperparameters, we can obtain a more accurate initial point cloud for this next frame. After refining the positions in S2, we can compute the top k closest points in S1 and choose the average of their corresponding spherical harmonics parameters as the initial radiance field parameter pi. So again, they're doing the average of the top k closest neighbor. So there's a lot of kind of averaging and downsampling that they're doing at various steps here, right? So because they have this point cloud, they can kind of at any point in time, they can say, let's take this point cloud of 1,000 points and reduce it to a point cloud of 100 points by basically doing a nearest neighbor and average. So it's constantly using that approach to kind of downsample the point cloud and then move from there, which I think is how they're achieving this kind of speed and memory efficiency improvement. Okay, so let's look at table 1 here and figure 4. So in table 1, static novel view synthesis evaluation on the synthetic Blender datasets is probably just a dataset they made in Blender. Back up. We evaluate the proposed method and comparable baseline approaches for novel view synthesis on static Blender scenes. The proposed model does not require an extra dataset for pre-training and improves on existing methods in training for speed and model size. Planoxel's paper, higher quality but bigger. Okay, so they're comparing theirs right here, ours, right, the approach in this paper, to I guess the original NeRF paper, a different NeRF implementation, and then here the Planoxels, and then there's two here. There's Planoxel and then Planoxel_S, which I think is a small version of Planoxel. Yeah, so you can see that the small version of the Planoxel trains in 8.5. The larger version trains in 11, but this paper trains in 3 minutes. So you kind of see an order of magnitude there. And inference, which is basically how fast can you run it, right? So this is the training time, and then this is actually the inference time at runtime. So 18 FPS for Planoxels, 32 FPS for this paper, and NeRF is 0.01 FPS, right? Like very, very slow. But this is the original NeRF implementation. I think it's much faster now. model size. So you can see here, the big planoxyl model is really big. It's over a gig. The NeRF model would be 14 megs, relatively small. And then this paper as well, also relatively small, 9 megabytes total. And then to measure or to kind of quantify the quality of the rendering, they use a couple different metrics here. PSNR, SSIM, LPIPS. So lower is better, higher is better. That's what these little arrows mean. They basically mean in this number, higher is a better number. And here in this number, lower is a better number. So these aren't necessarily great, like these kind of quantitative metrics for quality are usually a little bit misleading, so you're actually better off just looking at the actual images. So let's go ahead and do that. We have here a ST NeRF and NeRF T, so two different implementations of NeRF. So here on this column here, we have NeRF T. In this column here, we have ST NeRF. And then here we have the proposed work. So you have two guys kind of walking towards each other. And I think the big difference here is in the kind of crispiness, right? Where here you can actually see the glasses on this guy. Here you cannot. Here in both of the NeRF papers, there's kind of these weird artifacts that look like kind of mist clouds. But in this work, you don't have any of those artifacts. And I think that, to me, the reason that they don't have that is all this filtering that they're doing, right? So they're constantly removing outliers and kind of averaging all the points and then kind of reducing the points. So they're constantly pruning this point cloud, which is why theirs doesn't have any of these artifacts, right? NeRF doesn't have any kind of pruning like that. It has regularization terms that try to reduce the diffuseness, right? And that try to kind of force all the points to be on a surface, but it doesn't have this kind of explicit filtering and reduction that you're seeing in this paper. Okay, assessment. We evaluate the proposed point-based radiance representation for the novel view synthesis task in two scenarios: static scenes and dynamic video scenes, right? So both scenarios, we assume that the measurements from multiple views are available as input. In this section, we validate that the proposed method outperforms existing methods in computational efficiency while allowing for rendering high-fidelity images. Okay, they use a single NVIDIA 2080 Ti GPU, and this is all trained in PyTorch. So this is actually quite bare bones. That is not an expensive GPU, and they're only using one of it. So this is very much a academic training budget, right? No A100s here. Okay, we test the proposed method on the rendered multi-view images from the Blender dataset used in NeRF. Okay, so there's a NeRF synthetic dataset made in Blender that they used for the original NeRF paper, and here they're basically reusing that same one. I think that's the this here, the little palm tree and this microphone. I think that's the dataset that they're referring to. This dataset provides background masks that are automatically extracted. Yeah, so that's the important point, is that with this synthetic dataset, the masks are perfect, right? Because you have an actual explicit 3D object in a scene, so you know exactly where the outlines of that object are. Versus in a real-world scene with real-world data, you would not have that. Knocked over the mirror. So if you didn't have that, then the mask wouldn't be clean, and you would probably have some artifacts. We note that PBNR requires pre-processed geometry information such as point clouds and point features retrieved from conventional structure from motion, what SFM stands for. In contrast, the proposed method is network-free and learns both point cloud positions and appearance without the need for separate input geometry. computational efficiency and low memory footprint of the proposed point-based representations allow it to explicitly represent challenging dynamic scenes better than implicit methods that rely on networks to produce time-conditional outputs. Yeah, so kind of what we were saying, where as soon as you get into video space, you kind of explode the amount of training and inference time. So 1,000 frame video, which corresponds to 40 seconds at 25 FPS, requires then more than 20,000 GPU hours to train. So that's basically impossible. And more than 1 terabyte of storage for a 40-second NeRF video. While effective in reducing memory, this comes at the cost of rendering quality compared to frame-by-frame modeling. We evaluate the method on the video view synthesis from ST-NeRF and the human motion dataset. Okay, so now you have two different datasets that they're using here. They have ST-NeRF and then they have human motion. I think we're doing red for datasets, right? Both of these two datasets contain background masks that are generated via a segmentation network and color thresholding. So this is the mask that I was talking about, where now these aren't going to be perfect masks. So see how that impacts. The dataset features 16 camera views distributed uniformly on a semicircle. Okay, so this is one of the camera, kind of like these camera spheres that they have in computer vision labs. Quantitative evaluations. So this is on the data set that is real and that has the messy real-world masks and not the perfect synthetic masks, and you can actually see that they're doing quite well on that as well. Although it is comparable, 32 to 24, it's all very comparable here. Okay, and then here, ablation experiments. So this is a little bit more interesting. They're going to try to remove. So in an ablation experiment, you're removing different parts of your pipeline and then seeing how important those different parts of the pipeline are towards the overall final quality of the results. So they do 3 different ablations here. They do without the spherical harmonics, without the spherical harmonics per point, without the coarse to fine strategy, and without the filtering function. So you can see here, the difference isn't huge. None of these are necessarily making or breaking, right? Like 27, 26, 29 compared to 30. So all of them are contributing a small amount to the final result, is what I would kind of glean from this table. Yeah, table 3 shows that using spherical harmonics, the coarse to fine strategy, and the consistency filter function jointly achieves the best view synthesis. So using all of them does results in the best approach, or the best results. Conclusion. Departing from volumetric representations of scene radiance extensively explored in recent neural rendering work, we investigate an alternate radiance field representation that is based on points without giving up end-to-end differentiability. In contrast to coordinate network representations that require ray marching with hundreds of network evaluations per ray. So, again, this is just them bringing up the biggest Achilles heel of the current NeRF-based methods. Proposed methods, it's 2 orders of magnitude faster in training and inference time, while being on par with quality, or even better, according to their results here. Future directions that may build on the approach introduced in this work could include hybrid point surface models or combine the proposed rendering methods with point-based physical simulation methods. So this is the original NeRF dataset here. This drum set is probably seen it a couple times now. more more examples of kind of the fine details. You notice how like the biggest problem that kind of all of these neural rendering methods have is that they make the final image diffuse, right? Compare the crispiness of this ground truth image here for the Lego wheel to like all the subsequent ones. There's this kind of this natural diffuseness that happens. So this is the DSC dataset here. Old dataset, 2009. And they're kind of showing how the proposed method actually performs really well. And this is the real world mask that I'm talking about here. So look at how much more messy this mask is, right, around this person. There's so many pixels that like the mask goes into their head and kind of around their arm. Not very good compared to the mask for the NeRF dataset. Like look how much cleaner the mask is here in the NeRF dataset. It's perfect. Point cloud visualization. So these are the point clouds over time. So this is what it starts with, right? And then over time, right, they're doing their course define point cloud where they're kind of like using the average of the k neighbors and pruning the point cloud and then adding more points and then pruning it again and then adding more points and then pruning it again. And then over time, your point cloud represents more and more the object. And that's it. We're at the end here. Cool. So a nice little paper out of Princeton here. Interesting stuff. I think this kind of explicit representation of scenes is useful. I think that in a lot of these volumetric representations, it's very difficult to know exactly what the neural net has learned and exactly what is going on. But when you have explicit point clouds like this, you can actually start to you can look at that directly and determine, okay, where are the surfaces, where are the objects, and so on. And then maybe you can start layering physics on top of that, which is something that you'd need to do if you ever wanted to put this in simulated worlds, such as video games or VR or any of that. So it does seem like they're getting speed improvements, and the quality is actually quite good. So I'm interested to see where this type of research goes. Thank you